So, all right, thank you for patiently uh, waiting here. And I had to create a new stream because the last stream actually got completely messed up because of the internet connection. So, again, I'm starting from the very beginning because we only had 10 minutes. Really. All right. So, I'm starting from where we actually left off, right? All right. So, here in this part, what we are going to learn, so we are basically going to learn the mathematical background that we actually need in our control system engineering theoretical classes, and this is one of them, right? So we are going to we are going to acquire some knowledge on ordinary linear differential equations. We are going to learn some things about Laplace transform. Again, we have already studied Fourier transform in one of our earlier courses, signals and systems, so I'm skipping that here. And also we shall need some knowledge on linear algebra as well. So again, the mathematical backgrounds will be cleared up before actually we use the mathematical techniques as tools for our purpose, right? So here in this part, in this section, we are going to talk about Laplace transform, right? And we are going to introduce Laplace transform as an extension of Fourier transform. So essentially what we are going to do here, we are going to express rather express Laplace transform or rather we just wrote that, right? So let's define the Fourier transform. See, and as usual, if you have any query, feel free to ask. Okay, all right. So the point is, this is the definition of Fourier transform, and again I'm explaining what I'm writing here, right? So you have seen this expression, right? So you have seen this expression, you have used this expression, right? The point is, this signal that we are calculating the Fourier transform of is expressible or rather representable as the sum of sinusoids. So that's basically the cornerstone of Fourier transform, right? And Fourier series as well. So if this xt is a periodic signal that can be expressed as a sum of sinusoids, then we get a Fourier series. And Fourier series is essentially the representation or the representation of the constituent sinusoids, right? So if my signal can be expressed as a sum of sinusoids, then if the signal is periodic, then the Fourier series essentially gives you the constituent discrete sinusoids. And if the signal is aperiodic, then we would have a continuous spectrum of sinusoids, and those are represented by the Fourier transform. So again, for periodic signals as well, you can calculate the Fourier transform. We discussed all these things. But the main point to take away from this is that the signals for which we calculate the Fourier transform, or rather we can calculate the Fourier transform, should have or should be able to be expressed in terms of sinusoids, right? So if I give you a signal that is not expressible as a sum of sinusoids, then I have a problem, okay? Because Fourier transform, does not always exist. So I cannot just get any random signal or a random function, take any arbitrary signal or function and expect to have a Fourier transform, right? The signal must have a representation in terms of sinusoids. Then only we can think about that. And there are two conditions for that to be so. So one is the necessary condition, or let me start with the sufficient condition. Okay, so these are known as the Dirichlet conditions. Okay, named after Gustav Dirichlet. Okay, Dirichlet conditions. And what are sufficient? And again, let me just remind you what these Dirichlet conditions are. So first of all, there are three conditions imposed on the signal. One is that the signal has to be bounded. So xt must be bounded. So at no point in t the signal is allowed to go to infinity, right? Something like that is not allowed. Okay, xt should have finite number of discontinuities. I'm writing finite number of finite discontinuities. And number 3, xt should only have a finite number of local extrema in any bounded region. So what I mean is that xt is not allowed to go to infinity. Okay, if that happens, then the sufficient condition is violated. Okay, xt must have finite number of finite discontinuities, so only jump discontinuities are allowed, and xt should have finite number of extremas, so number of maximas and minimas, that the local maximas and local minima that the signal can actually attain should be finite within any given bounded region in t, right? Within any bounded interval in t. Rather, instead of saying region, I would say interval, right? So these are the sufficient conditions, right? So now these three taken together are known as the Dirichlet conditions, and Dirichlet conditions are the sufficient conditions for existence of a Fourier transform. So what I mean is that if I have a signal that satisfies all these three conditions, then it is guaranteed that the signal will have a Fourier transform representation, which means that if the signal satisfies these three conditions, then I will definitely be able to find a Fourier transform representation. The signal is definitely representable as a sum of sinusoids, right? So that's the sufficient condition. So if these conditions are satisfied, then a Fourier transform is guaranteed. So sufficient condition essentially means satisfying these so guarantees are just right, guarantees. The point is, if these conditions are satisfied, then we definitely have a Fourier transform. But these are sufficient conditions, which means even if some of these conditions are kind of violated, we still might have a Fourier transform, right? So sufficient condition, that is how sufficient conditions work, right? If the function or the signal satisfies the sufficient condition, then it is guaranteed to have a Fourier transform. But if any of these is violated, then you can still have a Fourier transform. I don't really know. But for that, we have something called the necessary condition. So what is the necessary condition? Question is, what is the necessary condition? The necessary condition is the absolute integrability of, so we say the necessary condition is this: absolute integrability of xt. And what is this absolute integrability thing? This absolute integrability essentially is this expression. Right. Let me just write it here. So this is the necessary condition. Now point is, you have two types of conditions, behind the existence of a Fourier transform. You have a necessary condition and you have a sufficient condition. The point for what is a necessary condition? A necessary condition is that a signal must satisfy this condition in order to have a Fourier transform representation. If a signal violates this condition, if a signal violates the necessary condition, then it is guaranteed that the signal will not have a Fourier transform representation. It is guaranteed that that signal will not be expressible as a sum of sinusoids. Do you understand the difference? So for the necessary condition, if the necessary condition is violated, then it is guaranteed then that the signal will not have a Fourier transform representation, right? And if the sufficient condition is satisfied, then it is guaranteed that the signal will have a Fourier transform representation, right? So I might have a signal that satisfies the necessary condition, but that satisfies the necessary condition, and if the signal satisfies the necessary condition, I would say, okay, there might be a possibility of a Fourier transform representation, but that is not guaranteed. But what guarantees a Fourier transform? This one, this sufficient condition, right? So a signal might be in between. It satisfies a necessary condition and does not satisfy all the sufficient conditions, right? But the signal might still have a Fourier transform. But if the signal violates the necessary condition, then it is guaranteed that the signal will not have a Fourier transform representation. And if the signal satisfies the sufficient condition, then it is guaranteed that the signal will have a Fourier transform representation. So that is how necessary and sufficient conditions in mathematics work, right? So if you satisfy the sufficient condition, it is guaranteed to be positive. And if you dissatisfy the necessary condition, then it is guaranteed to be negative, right? So I say, if you, and if, for example, if xt does not satisfy this, then x omega, that is the Fourier transform, does not exist. Right. So that's the point. So this is the necessary condition. Now, if we can think about signals that violate this sufficient condition, but what we would have a set of signals that do not have Fourier transform representations, right? You get the point, right? So that was one of the major drawbacks being figured out by Laplace himself. So when Fourier actually submitted his work to Laplace, so Laplace saw that you generally have a lot of signals that do not fall into this category, right? You generally have a lot of signals that cannot be expressed in terms of a sinusoid. So popular examples, okay, examples that dissatisfy the necessary condition itself. So if I have a signal that dissatisfies the necessary condition, okay, that does not satisfy the necessary condition, will not have a Fourier transform representation. So that is the main problem. But unfortunately for our control system course, we will see that we would encounter quite a lot of signals that would actually fall into that category where the necessary condition is actually violated. Okay, the necessary condition is violated. Okay, let me give you an example. So examples of signals that are not absolutely integrable. All right, so let's consider a simple example. For example, we have, say, for example, a typical ramp signal, right? So RT, what is RT? RT is essentially TUT, that very simple benign signal that you can have. This one, okay, you know this signal, right? That very simple signal. So that's xt. and this signal looks like this. All right, that very simple signal is not absolutely integrable, and you can see that for yourself. So for example, if I want to do the absolute integration on this, so what is absolute integration? This one, right? So I would take a mod on this and do this integration. So if I do calculate this, look carefully what happens. So I essentially have this tut dt. Now of course this ut dictates that when t is less than 0, the signal is 0. So I can change the lower limit to 0, right? Because before t equal to 0, the value of the signal is 0. So as it can be seen from here. So I do not really need to put that. So here I am putting infinity, and of course ut has been gotten rid of dt. And if we integrate that, what we essentially have is t square by 2, upper limit infinity, lower limit 0. This essentially goes to infinity, right? This is not finite. So this signal is not absolutely integrable. And just like that, the simple ramp signal actually violates the necessary condition for the existence of a Fourier transform. So this signal cannot be expressed as a sum of sinusoids. This signal does not have a Fourier transform. So that is, so we can infer, therefore RT, that is the simple unit ramp signal, that is the ramp signal, does not have a Fourier transform. Yes, FT short for Fourier transform. Let's take another example. So this is our example 1, right? So for example, this is example number 2, for example, right? A very simple example. Let's say the signal is as simple as e to the power t ut. A simple exponential signal. What does it look like? Again, I have written ut to make it causal, to make sure that the signal does not exist before, the value of the signal is 0 before t is equal to 0, right? So we are ensuring that. Right? And this signal has a 0 value there, and it jumps to a value of 1 at t equal to 0. And from there, it rises up, right? So this is the value of 1. Right? So that's your typical exponential signal, right? So that's also fine and all, but problem is this signal also violates the necessary condition for the existence of a Fourier transform, right? So if I again calculate the same thing on this signal as well, so this is the absolute integration. Why we say absolute integration? Because we are taking the absolute value, the mod, right? On this, again, this signal is positive throughout, and because of ut, I have to integrate from 0 to infinity, right? Because the negative values of t, for the negative values of t, ut is 0. So this integration is going to become like this. So we would essentially have the same problem, right? So the integral is e to the power t, and the upper limit is infinity, lower limit is 0. So this again tends to infinity. So essentially this also violates the necessary condition. And again, I told you, if a signal violates the necessary condition for the existence of a Fourier transform, then a Fourier transform will not exist at all. It is guaranteed that the Fourier transform will not exist, right? So these very simple basic signals, like an exponential, like a ramp, these signals are examples of signals that are quite common, right? These are nothing unusual. There is nothing unusual about these signals, right? But these signals are so common in control system engineering, but unfortunately they do not have Fourier transform representation, and that is why we have to resort to actually Laplace transform. So we will see how Laplace transform actually gets around this issue and figures out a way of dealing with signals like this. Okay, so signals that often do not have a Fourier transform, signals that are like that, like this, can be expressed in terms of a Laplace transform. So I'm going to explain why So again, just so therefore, essentially it means that e to the power tut does not have a Fourier transform, right? So I think this idea is clear. So if a signal violates the necessary condition, it is not going to have a Fourier transform. Now what is the problem? Where is the problem? The problem, look at the definition of, let's go back to the definition of a Fourier transform, right? So if xt is a signal, I'm assuming, again, I would encourage you to go back to the class where I actually talked about how we express this in terms of complex sinusoids. But the point is that if xt is expressible in terms of a sinusoid, in terms of sinusoids, then we can kind of write something like this, right? We can so we would be able to actually express the signal as a sum of sinusoids, right? So these are pure sinusoids. So if I write e to the power j omega t, that's nothing but cos omega t plus j sine omega t, right? Something like that. The point being, if I express a signal as a sum of sinusoids, the sinusoids in the complex domain can be written as e to the power j n omega t, something like that, right? E to the power j n omega t. Okay, do you understand the problem here? Right. Now, if I ask you, okay, I am thinking about this signal, this very simple exponential signal. The problem was that this signal was not expressible as was not expressible in terms of a Fourier transform because this signal was not absolutely integrable. But what if I am allowed to multiply something with it? What if I am allowed to multiply something with it? So the point is this. What if allowed to multiply something with xt to make it absolutely integrable? What if I'm allowed to do that? So this is what Laplace actually figured out. Laplace figured out that even if I give you a signal that is not absolutely integrable like that, but if I am allowed to multiply something with that, I might still get a signal which is absolutely integrable. So hold on, my cat is interrupting. I'm going to be back in a second. Unfortunately, the name of the cat is not Newton, and I am not Professor Shonku, right? All right. So, so again, let's get back to the question. What if I'm allowed to multiply something with the signal to make it absolutely integrable? Let's think about it. Okay, let's consider the exponential signal. That very simple example of an exponential signal, right? Okay, what if I'm allowed to multiply something with that to make it absolutely integrable, right? Or rather, let's start with the ramp signal. So this was our signal, right? Our signal was t ut. Now what if I'm allowed to multiply something with the signal so that this becomes absolutely integrable, right? This becomes absolutely integrable. So let's think about it. What can I multiply with this signal so that it becomes absolutely integrable, right? So let's think about that. So I have to multiply something, right? So I'm writing multiply something, right? So I have to multiply something to make it absolutely integrable. But think about it. What does absolute integrability mean? Absolute integrability essentially means that the area under the curve is finite, right? The total area under the curve is finite. Now look at this one, right? Look at this one. So if you look at this one, is the total area under the curve finite? No, actually the total area under the curve is not finite, right? The area is increasing gradually, right? Right? That is understandable. So the area under this curve is not finite, and because of that, the signal is not absolutely integrable. So what does absolute integrability mean? Absolute integrability means that the area under the signal must be finite, right? The total area under the signal must be finite, for example. So this is not absolutely integrable simply as I go along in the time axis. What happens? I have more and more area to sum up, right? So this signal is not absolutely integrable. Okay, what about the exponential? What about the ramp? Sorry, what about the ramp? I have the same problem essentially. So as I go along in this direction, the total area under the curve is infinite, right? You get the point. All right. So I have to come up with a way of multiplying something with the original signal such that this becomes absolutely integrable. This turns into a signal that has a finite area under it, finite total area under it. Do you understand my point? Okay, what is this integration looking for? This integration is essentially looking for the total absolute area under a curve, or total absolute area under a signal, right? So if I can somehow manage to multiply something with a signal such that the total area under the signal, total absolute area under the signal becomes finite, then I'm successful in satisfying the necessary condition, right? Do you understand what I'm saying? So with that said, the point is I have to multiply something, or rather, do I? I have to actually divide this signal with something. So what is the best thing that I can divide the signal with? Okay, try to understand. Look at the signal. Look at the signal here again. Uh, Again, why am I teaching you all these things? Because to make the idea intuitively clear, where does actually the Laplace transform come from? Yes, yes. Someone is saying, how can I ensure that by multiplying something, I would have a finite area, right? And I am going to tell you how you ensure that. How you ensure that. Now let's go back and look at the signal. What kind of signal we are dealing with right now? The signal we are dealing with right now is a ramp. So ramp would be the best example. And again, I would encourage you to do the same thing for the exponential, right? So this is the ramp signal. My god, the cat is once again interrupting. Hold on, huh? Hold on. Really sorry for this. So we have had so many interrupts today. Anyway, so that's a 0, right? Alright, so that's the ramp signal. So the ramp signal actually grows linearly, right? So this signal has a what we say is has a linear growth, right? That's understandable. This signal has a linear growth, so this area is growing actually linearly, right? Alright, something like that. So now try to understand that. So again, you understand the term linear growth, right? So the area, the signal is actually growing linearly, right? So this has a linear growth. Now instead of multiplying something, say I divide the signal. What if I divide the signal instead of multiplying something? Okay, say instead of multiplying something, I am dividing the signal. So I'm divide this with something. Same, I'm dividing the signal with something. Okay, so I'm not multiplying the signal, but I'm dividing the signal with something. Something here is a signal or a function that will possibly grow even faster than this signal can grow. Let that sink in. I'm trying to divide the signal with something or an expression or a signal or something like that, such that that portion actually grows even faster than the ramp signal here. So ramp signal grows linearly, but I want to divide the signal, or rather I'm trying to divide the signal with another signal which grows even faster, which grows even at a faster rate, right? So try to understand the point here. So let me think about a signal that grows even faster than this. Oh yes, I know, it's an exponential, right? If I take a positive exponential, then and if I choose proper parameters, then I can say if I take an exponential, okay, then that exponential will grow even faster. So this is something like e to the power, say, I don't know, e to the power t, right? And this is rt. That's not e to the power t, huh? Sorry, really sorry. That's e to the, this is e to the power t. So this is e to the power t, and that's t ut. Now try to understand, this signal is growing even faster, right? Maybe my drawing is even not that correct really, because exponentials do rise up pretty quickly, right? Their value actually goes up substantially very quickly, right? Okay, so the point is that I can, right off the top of my head, I can figure out a signal that I can divide this signal with, so that I have in the denominator I have a signal which rises faster than this signal can rise. Got the point? So what if I think about this kind of signal, say e to the power t? What if I think about something like this? And what if I divide the original signal, which was tut, which did not have a Fourier transform? What if I take that original signal tut and divide it by e to the power t? What if I what if I do something like that? Question is this signal now absolutely integrable? Is this signal now absolutely integrable? Do you understand the point? Okay, so instead of directly calculating the Fourier transform of a signal, we are trying to figure out if we can multiply something with the signal such that the signal is now absolutely integrable. Okay, so now what does the signal look like? Let me just draw the signal here so that you have some visual grasp on this. Again, this is the product here now. So this is my xt divided by e to the power t, right? So now again, so that was your xt, right? So now if I do this division, see, as you can see, when the value was small, when the tut value was small, this was also pretty much small. But when this value was larger, when TUT was large, e to the power t was even larger, right? So as I go along in the positive direction of the time axis, I would have even larger denominator, right? So this will grow, this grows, but this grows even faster. This one grows, but this one grows even faster, right? Much faster rather. This one grows much faster, right? So intuitively we can see that as time goes on, I am dividing this signal with even larger numbers, and as such, if I plot this, I mean these two, if I take these two signals and if I plot them, the plot is kind of going to look like this. So initially the value would be 0 at this point, but initially the denominator would be small comparatively, and then the denominator is going to become larger and larger, and this will be kind of the signal we are talking about. So this is essentially the plot of TUT divided by e to the power t, right? So essentially now you can think about this, that okay, what about the area under this curve? Does it look infinite anymore? What about the area under this curve? Does it look infinite anymore? Okay, my cat is once again interrupting somehow. Okay, question is, does this area look infinite anymore? Does this area look infinite anymore? Of course not, right? As time goes on, the area diminishes, and of course the sum is possibly finite. But let's see that for ourselves, right? Let's calculate the absolute integral for this. Okay, so what is the absolute integration? Minus infinity to infinity, and then TUT divided by e to the power t. Okay, someone is saying, can I explain the last part? Okay, so here what I am trying to do, see, question, why was this signal not absolutely integrable? Because as time went on, the area under the curve became larger and larger, so the area under the curve was not finite. So again, what does this expression give you? What does the necessary condition give you? It asks, it essentially checks whether the signal has a finite absolute area under it, right? Finite total area under it, right? Okay, so now this signal does not have a finite total area under it, right? As you go on along the time axis, you have infinite area essentially. You have infinite area essentially, right? Right? So now Laplace thought, okay, fine. So these signals would not have a Fourier transform because they are essentially violating the necessary criteria of Fourier transform, right? So they won't have a Fourier transform. But what if I'm allowed to divide the signal with a term which grows even faster than the speed of growth per se for this one? So this one was growing. So for example, take this one. This was the ramp. This one was growing pretty fast. But what if I can divide this signal? What if I can divide TUT with something that grows even faster? That grows even faster, right? So here is that one. So I have divided TUT with, or rather by, e to the power t. So I have divided TUT with e to the power t, right? Divided TUT by e to the power t. And as such, e to the power t grows faster than TUT can grow. E to the power t can grow faster than TUT can grow. So I have just plotted them in a same plot to show you that same thing, right? At t equal to 0, the value of this signal is 0, but value of e to the power t is 1. But as time goes on, e to the power t has larger and larger values compared to this, right? Right? So of course, for example, when t is 50, when time is 50 seconds, TUT has a value of 50. But what is e to the power 50? E to the power 50 is this large, right? A huge number. So you can imagine, as time goes on, what happens? I am dividing with larger and larger numbers. So the point being, TUT grows, right? So for example, when T is 50, say, when T is 50, on the numerator I have 50, but on the denominator I have e to the power 50, and e to the power 50 would be humongous, right? So in the denominator I have a very large number that I am dividing the signal with, right? So as time goes on, I am dividing this signal, the ramp signal, with larger and larger values. I mean larger and larger values, so large that this ramp signal can't even cope up. So this is essentially the plot of this one, TUT divided by e to the power t. So if you plot that, again you can use Python to plot this. Okay, this is what the plot kind of looks like, right? So now if I now ask you, what does the area under this curve look like? What does the area under this curve look like? Okay, does it look infinite like the original ramp? So original ramp had an infinite area under it, but does this one look like an infinite area? The answer is no, of course. The area kind of looks like a finite area, right? But let's verify that, because in mathematics everything is concrete and verifiable. So let's write dt. Everything here is positive, so I can get rid of the modulus sign here. And of course, by virtue of the ut, I can take the limit from 0 to infinity, because when t is negative, ut is 0, so the whole signal itself is 0. And so I essentially have t divided by e to the power t dt. That is something I am integrating right now. Okay, that's fine. Okay, right. So integration from 0 to infinity. So what I have is t e to the power minus t dt, right? Now of course we can now integrate this. Can we integrate this? Of course. Let's find out the primitive by using something called the rule of partial fraction. Sorry, rule of partial integration, right? Integration by parts. And so essentially we would have minus t e to the power minus t. Of course you people can do this yourself, I think. All right, so if you do a partial fraction expansion, so that is something you're going to get, and this is going to be minus t e to the power minus t 0 to infinity, and plus this is going to be again minus e to the power minus t 0 to infinity, right? All right. So now if you put the upper limit here, think about it. So if you put the upper limit here, what do I have then? If I put the upper limit, so what I essentially have is t. Let me just write this down again as this one. This is t divided by e to the power t, and would have limits infinity to 0 and minus 1 by e to the power t 0 to infinity, right? All right. So if I put infinity here, okay, somebody asking something. No, you have just messed up the definition of ut. You have just messed up the definition of, yeah. Why did ut go? Ut went into this story, right? So ut has a value of 0 when time is less than 0. So essentially this integration, I have just reduced the lower limit from minus infinity to 0. Because when t is negative, the value of this whole signal is 0 because of ut. That is where ut went. Ut has a value of 0 when t is less than 0, right? And afterwards, it has a value of 1, right? So here, look at this one. So when I put infinity as the upper limit, look carefully what I have. I have t, so a very large number, infinity, divided by e to the power infinity, like that. So an even larger number, right? So think about infinity as 100, say. So if this is 100 in the numerator, then in the denominator I would have e to the power 100, right? So I don't think about infinity, think about this. So if I have 100, then I have e to the power 100. So which one is larger? Of course e to the power 100 is way larger than 100, right? So what about this one? right? 1000 is large, but what about e to the power 1000? That's even larger, way larger than this. So essentially, as t goes to infinity, t by e to the power t, this limit approaches 0. So the upper limit is 0 minus, what if I put the lower limit? If I put 0, then t is 0, e to the power 0 is 1, so I have 0 again, minus. Now again, same thing here. If I put the upper limit here, then I have 1 divided by a very large quantity, so that's a 0, minus, and if I put 0 here, then I have 1 divided by 1, so I have this. So essentially the answer is 1. The point is, we have now been successfully been able to convert the ramp signal into something that is absolutely integrable. See, look very carefully what I just did. So we started with a ramp signal. That is, we started with a ramp signal such that this integration was diverging, right? This was not finite. But by virtue of dividing the signal with a suitable value, suitable function, we have now made this finite, made the absolute integration finite, right? So all we just changed was this multiplication factor, right? So ut went into there. So whenever you have ut, think about that. Ut has a value of 0 when t is less than 0, right? So essentially the limit cuts down to 0 to infinity, from minus infinity to infinity, by virtue of ut, nothing else, right? So look at the very important point here. I have been able to multiply this signal with a value here, like that, such that the total area under the curve is now finite, no longer infinite, right? And of course you can figure out, you would be able to see, yeah. So yes, the funny thing is that this one says it can get rid of 99.99% of germs. But before this I used to see 99.9%, but this is even better, 99.99%. keep that in mind. Alright, so in the same vein, can we say that of course you can do it yourself. I mean, this will also be true. If I do this integration, that is also going to be finite. Okay, you can check it for yourself. Okay, this is also going to be finite. Right? This is also going to be finite, right? Similarly, just like that, I can say I can have e to the power sigma t. I can divide tut with by e to the power sigma t and have a finite value, right? As long as sigma is a suitable real number, right? The point is, so if sigma is 2, 3, 3.5, anything, any positive real number, as long as this sigma is any positive real number, I would have a finite value here, right? Try to figure out the point, right? You can do the integration yourself and see that it is actually true, right? So as long as sigma is a positive real number, I would have a finite value here. I mean, it does not have to be positive always, but yeah, in this particular example, it will have to be a positive real number, right? So that's what I'm saying. Sigma is a suitable real number. When sigma is a suitable real number, I can now do this. So let's sum up what we just did. And this is fine, right? You can do the integration by yourself. Let's sum up what we did. Okay, step by step. So in the first step, we saw that this signal TUT, which is the ramp signal, is not absolutely integrable, right? So we saw that TUT is not absolutely integrable. Okay, then we thought what if we divide TUT, rather that's XT, right? It's just X, right? XT. We saw that XT is not absolutely integrable. Then we thought, what if we divide XT by something that makes it absolutely integrable? What if I am able to divide XT with something that makes it absolutely integrable, right? And by looking at it for a while, we saw that we can divide XT by e to the power sigma t, where again sigma is a suitable, again I'm going to explain the suitable term in the next class, okay, where sigma is a suitable real number. Again, in this particular scenario, the suitability simply meant that sigma was a positive real number. It only meant that. Okay, sigma is a suitable real number. So, and by looking at it for a while, we saw that we can divide xt by e to the power sigma t, where sigma is a suitable real number, to make it absolutely integrable, right? So the point is, this signal itself wasn't absolutely integrable, but this signal, so this signal is absolutely integrable, right? This signal was absolutely integrable, so this was finite. So let's just say finite. Finite means less than infinity, so absolutely integrable, right? All right. Now, for the foreseeable part, let's forget about this and let's see that we can now, of course, say that this is xt e to the power minus sigma t dt. So that also is finite. So we have just brought the denominator's term into the numerator, right? So essentially what we know right now is that xt does not have a Fourier transform, right? So what we know particularly is that xt itself does not have a Fourier transform. This xt signal does not have a Fourier transform by itself because it violates the necessary condition for the existence of a Fourier transform. Okay, but what about this? But what about xt into e to the power minus sigma t? What about this one? This one at least satisfies the necessary condition, right? Let's think about the Dirichlet condition. Let's go back. Okay, try to understand. Xt by itself does not satisfy the necessary condition, right? So xt cannot have a Fourier transform by itself, right? xt itself does not have a Fourier transform. But what about xt into e to the power minus sigma t? What about xt into e to the power minus sigma t? Does it have a Fourier transform? Okay. So of course it now satisfies the necessary condition. What is the necessary condition? That xt into e to the power minus sigma t should have, the necessary condition is xt into e to the power minus sigma t should have a finite area under the curve, right? Finite absolute area under the curve, and that's true. So it is satisfying the necessary condition. Now let's see whether it actually can satisfy the sufficient conditions as well, so that we can guarantee a Fourier transform. Right? Right. Look at the signal very carefully. Okay, this is what we have. All right. Let's go back. What was the Dirichlet condition? Xt must be bounded. So xt should not have an infinite value. Right? So essentially the signal. Now this is my signal. This yellow one is the signal, right? Does it have any infinite value in it? No. The signal is bounded, right? It has an upper bound and a lower bound. The signal is bounded. Let's go back. Does it have a finite number of discontinuities? Okay. It has no discontinuity per se, but yes, if it did, it would be a finite number of discontinuities. Another condition, third condition, it should have a finite number of local extrema. So local minima and local maxima. So here we have a local minima at t equal to 0. Then we have a local maxima at some point here, right? And then the signal actually approaches gradually. So we have finite number of maximas and minimas, right? So this signal also now satisfies the three Dirichlet conditions. So TUT did not even satisfy the necessary condition. But if I divide TUT by e to the power sigma t, where sigma is a positive real number, I can make it not only satisfy the necessary condition, but also I can make it satisfy the sufficient conditions as well. So essentially, by doing this, by multiplying xt, which was the ramp in this particular example, by multiplying that signal with e to the power minus sigma t, in this particular example, sigma is a positive real number, but it could be some other type of real number. It's a real number. That's something you have to put in your mind. Is that this signal now has a Fourier transform, because it not only satisfies the necessary condition. What was the necessary condition? The necessary condition was the absolute integrability of the whole signal, right? It satisfies that, and we can retroactively verify that it also satisfies the Dirichlet conditions, which are the sufficient conditions, right? So now, even though xt did not have a Fourier transform, xt into e to the power minus sigma t, where again, once again, I cannot stress this enough. Okay, sigma has to be a suitable real number. Okay, here in this example, it has to be a positive real number. Any positive real number will do. Okay. Then this signal has a Fourier transform. So let me write it down for you so that you can actually follow properly. So what we have essentially derived is that xt does not have a Fourier transform, but xt into e to the power minus sigma t, again where sigma is a suitable real number, does, even though xt does not have a Fourier transform, but xt into e to the power minus sigma t does. Okay, as someone is asking, so can I apply the trick for every signal? And the answer is what should I say? The short answer is no. The short answer is no. The long answer is sort of. Okay. The long answer is sort of. The point is you need the xt. So the point is that this signal, this composition here, this product here should be absolutely integrable. So now somehow if xt is so xt rises so fast, then even an dividing it with an exponential, okay, even dividing it with an suitable exponential, still you cannot make the area finite. Then of course you cannot have a Fourier transform. you cannot have a Fourier transform, right? But I mean, if xt has a very fast rate of growth, in that case you cannot divide it with something suitable such to make the growth slow down, right? Point is, this has to grow faster than this, right? So that is the point. The point being, the signal xt, so this is xt, right? So this one is xt. So xt grows, but the point is I have to be able to divide it with some part of some type of exponential that grows even faster. That might not always be the case, but that's pretty much the case for many signals, many signals. So essentially what we have many signals that do not have a Fourier transform, but when I multiply them with e to the power minus sigma t, they do then have a Fourier transform. So this is the point. So there are many signals such that xt does not have a Fourier transform, but doing this, just multiplying that signal with e to the power minus sigma t, makes it have a Fourier transform, right? So let me change my statement here, rather modify my statement here a bit. What did I just do? So I can say there are many signals xt that does not have a Fourier transform, that rather do not have a Fourier transform, but this part will have a Fourier transform. So I'm asking, so other xt being exponential, can they say that multiplying yeah, so the point is that this signal, I mean, I haven't yet talked about Laplace transform. Have I talked about Laplace transform? No. I am still talking about Fourier transform. The name of the subject is Laplace transform, right? I'm still talking about Fourier transform. I haven't for a second mentioned, did I ever write Laplace transform here? No. Throughout the derivation or whatever we are doing here, I haven't discussed Laplace transform, right? So we are all still calculating Fourier transform, right? We are still trying to figure out a way of making a Fourier transform available for a signal for which usually the Fourier transform is not available, right? So if a signal is not absolutely integrable, so here there are several types of signals where the signal is not absolutely integrable, so the signal does not satisfy the necessary condition for having a Fourier transform. So the signal cannot be expressed as a sum of sinusoids, so it won't have a Fourier transform. But we can multiply the signal with e to the power minus sigma t, where sigma is a suitable real number, to make it have a Fourier transform, right? So far we have only talked about Fourier transform. Okay, so essentially what we can now say is that xt into e to the power minus sigma t has a Fourier transform. But question is, then what is the Fourier transform of xt into e to the power minus sigma t? What is the Fourier transform of xt into e to the power minus sigma t? Of course the answer is this. This is the Fourier transform of xt into e to the power minus sigma t. So this is the signal. How do you calculate the Fourier transform? Multiply this with minus j omega t and integrate from minus infinity to plus infinity with respect to t, right? And again, we derived Fourier transform happily in our previous semester, right? So this signal has a Fourier transform. Xt itself does not have a Fourier transform, but this signal has a Fourier transform. So, and that's the Fourier transform, right? That's the Fourier transform. Get the point, right? Okay, all right. Any query here? No, I don't think so, right? So that's the Fourier transform, right? Now, can I write that this is essentially minus infinity to infinity xt e to the power minus, and here I would have minus sigma t minus j omega t. So I have multiplied the exponentials, right? Okay, so I can say, I can take the minus sign factor out of it. I can say sigma plus j omega, and I can write t here, I can write dt here. Okay, so the way we used to write Fourier transform, so of course if this was like j omega, we would write x omega here like that, right? So instead we say that this is the Fourier transform. The Fourier transform would be a function of sigma plus j omega. It won't be just x omega, but it will be like a function of sigma plus j omega. So this is the Fourier transform of that. xt e to the power minus sigma plus j omega t dt, right? So this is the Fourier transform of xt into e to the power minus sigma t. Once again, I cannot stress this enough. Sigma is a suitable real number. Okay, right? So this is the Fourier transform of this. So I have just modified Fourier transform. But so this looks like a complex number, right? Something plus j something, right? This is like x plus jy. X plus jy is written as z, a complex number, right? So sigma plus j omega is simply written as s. Okay, so sigma plus j omega is written as s. Okay, so so let us write sigma plus j omega as s. So again, it's a complex number, right? So s is a complex number, just like having x plus jy equal to z. So that is the complex number, where x is the real part and y is the imaginary part. Just like that, we write x. So if I do that and write it here, what we essentially would have is xs equal to, let's just use this. So we would have xs equal to integration from minus infinity to plus infinity on xt, okay, e to the power minus st. So s is essentially sigma plus j omega dt. All right, so we would have that. This is known as the Laplace transform of xt. This is known as the Laplace transform of xt. So that is where Laplace transform comes from. So what happened is Joseph Fourier submitted his work to Laplace. Laplace rejected Joseph Fourier's work because he said that this Fourier transform, your idea, is not even applicable to exponentials. So there are many signals for which your idea is not applicable. So let me reject your work. So Laplace rejected Fourier's work, and then he did this modification and he published Laplace transform. So even though Fourier transform was originated earlier, Laplace transform was published first. Then again, you know the story of Fourier joining Napoleon's army and coming back, and then publishing his own work with his own money, but then still no one really recognized his work. Okay, but here the takeaway from this entire class is that Laplace transform is nothing but an extension of Fourier transform. So with that said, I can say, so this is pretty much absolutely true. Laplace transform of xt is equal to, or rather is the same as, the Fourier transform of xt into e to the power minus sigma t, where sigma is a suitable real number. So essentially, by proper terminology, we say, so L is used for representing Laplace transform. So Laplace transform of xt is identical to the Fourier transform of xt multiplied with e to the power minus sigma t. So that is what you have to understand. So this is where actually Laplace transform comes from. Okay, so this in particular is known as bilateral Laplace transform, and again I'm going to elaborate what I mean by bilateral, unilateral. This terminology will be elaborated in the next class. Okay, this is known as a bilateral Laplace transform. Okay, and the significance of S equal to sigma plus j omega will be also explained. Let me explain it in a bit. Okay, but again, tell me if you have if you don't understand something here. So the point being, we did not just randomly replace j omega with S, right? That did not happen. So this is how we derive the expression for Laplace transform. Again, I personally like to derive everything, right? So again, if you have any query, feel free to ask at this point. So point is, so what about S? So I see that we have written S equal to sigma plus j omega. So we know that omega is frequency, right? In the Fourier sense, right? So of course this j means nothing other than a factor, right? So this also has to be frequency, right? Because if omega has a unit of radian per second, then sigma also has a unit of radian per second, right? Then S also has a unit of radian per second. So all these terms here are frequencies, right? So this term is known as a complex frequency, or frequency in Laplace's sense, right? And this is the real part. Okay, and this factor actually determines how the frequency, how the complex frequency rather decays or I'm going to explain this later on. Okay, so someone is asking, how do I write x sigma plus j omega as a Fourier transform of this? Okay, this is the capital, right? So actually we have derived this, right? The Fourier transform of xt into e to the power minus sigma t is essentially the Laplace transform of xt. So that is what we have derived this, right? So we have derived this actually. We have seen how this actually turns out. We have derived this. So if you are joining late, so you can go back and follow along. All right. So again, if you have any query, feel free to ask at this point. Otherwise, we're going to end our discussion here. So I believe you now understand where actually Laplace transform comes from, right? Laplace transform comes from a simple extension of Fourier transform, where there are special classes of signals which do not have a Fourier transform because they violate the necessary condition for the existence of a Fourier transform. Namely, they do not have absolute area under them, right? They do not have finite area under them. So they can be multiplied with suitable exponentials that actually reduces their area such that they are finite in nature, and they then have Fourier transforms. So in that sense, we have this criteria here. So essentially, that is how we define Fourier transform, Laplace transform here, right? So we use this entire class to define Laplace transform. Again, this is going to be the definition of our bilateral Laplace transform. We are going to work along with this and figure out a few more things about it. But that's the end of today's discussion. Feel free to ask any question that you might have. So if you have any question, feel free to ask at this moment, and otherwise we are going to end the discussion, and I'll see you tomorrow probably, and we shall continue our discussion from here. Alright, so if you don't have any more queries, so we're going to end the discussion here. Thank you for being patiently waiting here. Like, we lost 40 minutes right at the onset of the class, and in any case, thank you very much. So that is how we have derived Laplace transform. This is how Laplace transform originated, right? As an extension of Fourier transform, sort of a better Fourier transform. Okay, so see you tomorrow, and we will discuss how we actually use this. Anyway, thank you very much, and I'll see you tomorrow again, once again.